In this video, I'll show you how to get from this to this. Welcome to my new series where I'm testing different methods to make 3D printed surfaces smooth by hiding the layer lines. This video is all about chemical smoothing, covering ABS, ASA, HIPS, PVB and yes, even PLA. I look into different ways to apply the smoothing agent and test how it affects technical parts. We'll be checking dimensional accuracy, scratch resistance and even layer adhesion to see if there's a functional benefit to all this. Let's get right into it here at JanTec Engineering. Thanks to PCBWay for sponsoring part of this video and to Prusa Research, the sponsor of my studio, which enables me to create all these videos. A friend and I recently built this mobile workbench, which you'll see throughout the video. 3D prints straight off the printer can sometimes look a bit unappealing. Depending on your design, print settings, material type and even filament color, layer lines can be quite visible, creating that typical FDM 3D printed look. For everyday prints, you're probably fine with it, but when it comes to gifts, cosplay parts, products you want to sell and so on, it's a different story. Then you should fix it. For a surface to behave optically smooth in visible light, its roughness should be much smaller than the wavelength of the light, so you don't get significant light scattering. I have no way of actually measuring surface roughness here, so I'll stick to inspecting prints under my studio light. As said, in this video we're going to go fully into chemical smoothing, covering how to smooth ABS, ASA, PVB, HIPS and PLA. Make sure to be subscribed to not miss my video about slicer tricks and mechanical sanding to hide layer lines. Now, in most cases, a material not being resistant to chemicals is considered a bad thing because it limits where you can use it. But for materials like ABS, we can actually use this weakness to our advantage. ABS dissolves in acetone, and that is exactly what makes chemical smoothing possible. Here's how that works in theory. When we get a suitable solvent in touch with the surface of a print, it begins to dissolve the outer layer of the polymer chains. This creates a thin, liquid-like layer of plastic on the surface. Because of surface tension, this liquid layer naturally wants to pull itself flat, filling in the gaps of the layer lines and rounding off the peaks. Once the solvent evaporates, the plastic rehardens, leaving you with a smooth, glossy and uniform surface. At this point, you might wonder, why can't you just remelt the surface with heat? The problem there is thermal conductivity. To get the surface hot enough to flow, the heat usually travels deeper into the part. Before the outer surface even starts to look smooth, the internal structure softens and the whole model begins to deform. Solvents are different because they only interact with the very outer skin. This allows the surface to liquefy while the core of the print keeps its structure. Before we can start smoothing our first prints, a few words about safety. I have to admit, I'm not known for working super safely in the past, and recently some of you mentioned that I should take this topic more seriously. And you're right. That's why I bought some more safety equipment. No, for real, wear proper PPE. This mainly includes a respirator and gloves when working with solvents. Also, keep in mind that most of these chemicals are flammable. Most of you probably know that polystyrene, used for foam packaging, dissolves almost instantly in acetone. Well, since ABS and ASA are partly made of styrene, they share that same property. For my tests with acetone, I picked a spool of ABS from my storage. As said, it also works with ASA, but I decided to go with matte ABS in Earth Grey from CR3D, a local German producer. I then loaded it into my Prusa XL and started printing a couple of these chest pieces I found on printables. The pawns have a spherical head, the rooks have sharp corners, and the green has some fine details, making them perfect for a smoothing test. I went to the hardware store to get some acetone and a box which functions as a vapor chamber. Make sure your container is acetone resistant. I guess you all know what can happen if you ignore that advice. Polypropylene is acetone safe, and most of these clear boxes are made from PP. For the first test, I placed a pawn and a rook on some metal nuts in a box and soaked paper towels in acetone. I put them on the sides and the top of the box, making sure they don't touch the prints. Then I sealed it up and set a timer for 1 hour. During that time, the acetone vapor from the towels should smooth the surfaces evenly. After about 30 minutes, I already noticed them getting smoother, and after another 30 minutes, I opened the box and removed the towels. When moving the box, the parts slipped off the nuts, but that's fine. I let them air dry overnight, and the results the next day were honestly perfect. I didn't expect my first try in years to go this well. The parts are really glossy and layer lines are completely gone. But let's be critical. While the sphere on the pawn looks incredible, we definitely lost some detail on the sharp corners of the rook. And since I know that a lot of you, including me, mostly print technical parts, I wanted to run a second test on these mounts I designed. Even though they look pretty good right off the printer, especially the top surfaces have some visible roughness. Acetone smoothing should improve this and might reduce friction where the gantry glides on the silver steel rod. By the way, if you're enjoying this deep dive, consider subscribing to my channel. So far, only a small percentage of you are subscribed. It really helps me out. Thank you. I repeated the process, but this time I used more stable standoffs and added the rest of the chest pieces to see how the chamber handles larger batch. I then again used paper towels dipped in acetone. Since I didn't have a fitting lid for this specific box, I used a piece of wood to seal the top. After the first hour, the parts were starting to look smooth, but I could still see some layer lines, so I decided to wait another hour to be sure. After about 2 hours total, they looked ready, so I removed the wood lid and let them air dry. One of the paper towels touched one of my prints. It's nearly impossible to remove once the plastic has softened, so learn from my mistake. Make sure you have plenty of clearance in your box so the towels can't move and touch the parts. Once again, the chess pieces turned out looking perfect, but let's analyze the technical parts. The surface quality definitely got better and the screws still fit exactly as intended. However, the rod actually glides worse than before. While smoothing probably decreased the friction from the layer lines, my assumption is that the geometry of the horizontal holes slightly deformed or shrank during the process. If you're doing this for mechanical parts, you might need to adjust your tolerances in the design process. Next, I wanted to test the scratch resistance. I tried marking the surface with a screwdriver and a cutter, and it feels a bit softer now. The scratches are quite visible. That's something to keep in mind. You might want to add some sort of protective coating after the smoothing. Because the layers effectively fuse together into a solid skin, it can significantly improve layer adhesion, which is tensile strength in that direction. Prusa actually tested this in their lab and their results showed about double the layer adhesion compared to regular samples. So vapor smoothing isn't just for looks, it can have real technical benefits for your parts, but make sure you're accounting for those slight changes in geometry. Before we get to smoothing PVB and PLA, a few words about the sponsor of this video, PCBWay. Most of you know them for PCBs, but they've actually become a one-stop shop for entire projects. Beyond just bare boards and full assembly, they handle the mechanical side too, covering everything from CNC machining and 3D printing to sheet metal and even injection molding. This is especially useful when your project needs both custom electronics and specialized hardware. Instead of sourcing from 5 different vendors, you can get your PCBs and mechanical parts all from the same place, PCBWay. If you're working on something complex and need professional grade manufacturing with short lead times, check out the link in the description. Thanks to PCBWay for supporting the channel. Next, I've got PVB. It prints and behaves similar to PLA with the difference that it can be chemically molten in IPA, which is less harmful than acetone and widely used in cleaning. I guess most of you already have a bottle standing right next to your printer. That makes PVB a very interesting material for smoothing. You can get Prusameters PVB in such a sample pack or on 500 gram spools, selling for around 45 euros, which is quite expensive. There are some other options available out there, but I feel like the demand for PVB is generally rather low, which probably leads to the higher price. Anyway, I loaded the orange PVB into my Prusa MK4S as it can be printed on an open printer just like PLA. I printed various test parts. You can find the models shown in this video in a printables collection. The material is a bit translucent, which I like, but the downside is that it makes the infill visible, which I'm not a huge fan of. Since I was running low on IPA, I ordered some more online and realized it's way cheaper per liter if you buy it in 5-liter packs or bigger. My recommendation is to grab one of those big packs, you'll end up using it from time to time anyway. The Prusa blog article suggests a few different ways to smooth their PVB. I decided to try vapor smoothing first, just like I did with the ABS, by hanging IPA-soaked paper towels inside a plastic box. For the large diamond, I tried brushing the IPA directly onto the surface, and for the small diamond, I fixed it with a piece of wire and dipped it directly into the IPA for about 15 seconds, then let it air dry for 20 minutes before repeating the process a few times. Now that all parts are dry, let's compare them to the unsmoothed prints right off the printer. The Bambu wave holder thing did get a smooth surface, but due to the translucency of the material, you can still see the infill. Same for the small diamond. For the large diamond, I suspect that brushing on one layer of IPA is not enough to fully smooth it, so the vapor chamber wins here. I think the results are a bit underwhelming. Maybe it was me and I didn't apply the IPA correctly. I remember working with PVB when it first came out from Prusameters with better results. I sprayed it onto the objects back then. Also, it works better for vase mode objects without infill, but I feel like that's a niche application. What are your thoughts and experiences? Let me know in the comments. When I started 3D printing back in 2016, there was basically no way to chemically smooth PLA. But recently at a maker fair, I managed to get a bottle of Elegoo, which is a smoothing agent specifically for PLA. Right now, it's not widely available worldwide, but I'm pretty sure it soon will be. I've also seen people experimenting with ethyl acetate in combination with heat and long exposure. I'll add some links to those articles in the video description if you want to check it out. For the Elegoo, the official instructions give you two ways to apply it. For smaller objects, they recommend the shaking method. You pour some of the liquid into a glass jar. A simple pickle jar works perfectly. Add the object and shake it for about 10 to 30 seconds. I found this to be a bit tricky in practice. It's hard to get the part back out of the jar without touching the now softened surface and leaving a permanent mark or scratch. I eventually fished them out and placed them on a sheet of wood to dry. The second method is simply brushing it on, similar to how I tried using IPA on the PVB earlier. I chose to only brush it on half of my test model so I could really see the side-by-side difference. After drying for 2 days, I came back to check the parts. Smoothing definitely works. On this sheet model, I only brushed one side of the face and you can see quite clearly how the layer lines vanished. My test diamond bonded to the piece of wood while drying, and as I mentioned, getting parts out of a jar without marking the surface and placing them somewhere to dry is a real challenge. But overall, I'm genuinely surprised. PLA is probably the most used filament in the world, and being able to chemically smooth it by simply brushing an agent onto it is a huge step forward. If this becomes more affordable and easier to find, it could be a total game changer for people who want a premium finish but don't want to deal with the fumes and warping of ABS. HIPS filament is also polystyrene, so you can smooth it with acetone, just like ABS. But it also dissolves in limonene, which is a citrus-based solvent. I've used HIPS as a soluble support material in a previous video, which you can check out on the channel if you're interested. So, based on my experiments, when should you use which technique? In my opinion, ABS or ASA with acetone vapor smoothing is still the gold standard. It's the most reliable, the most cost effective, and the results are the most consistent, at least according to my tests. However, if your printer can't reach the bed temperatures needed for ABS, or if you don't have an enclosure to manage the warping, PVB is a good alternative. It prints easily on almost any machine, and while my results today were a bit mixed, a simple IPA spray can give you a really unique, smooth and glossy finish. As for PLA, if you can get your hands on a specialized smoothing agent like the one from Elegoo, it's definitely worth a shot. Maybe as more options become available worldwide and the prices come down, smoothing PLA will become as common as smoothing ABS. If you know of any other materials or secret solvents that can be used for chemical smoothing, let me and the rest of the community know in the comments. As said, this was the first of a 3-part series on smoothing 3D prints. In the next 2 parts, I'll go all into designing and slicing for less visible or hidden layers, and then show you how to mechanically sand parts using filler and primer. So don't forget to subscribe to not miss it. Thanks to my channel members for your support. And thanks to everyone else for watching. See you in the next video here at JanTec Engineering.